Hi, hello. For this video, we're going to continue on the practical applications for operational amplifiers. Okay, so from the previous videos, we have discussed several applications such as inverting, non-inverting, unity gain, and then we had our summing amplifier, and then we had our differential amplifier. Okay, so for this video, we're going to discuss three more practical applications for operational amplifier. Okay, so the first application is what we call an integrator. Okay, so what does an integrator do? So an integrator is used to provide an output voltage which is proportional to the integral of the input voltage. Okay, so for an integrator circuit, usually our input is a DC. Okay, so our input is a DC level and its integral is a linearly increasing or decreasing ramp output. Okay, so depending on our input. So our input is a DC level and its integral is a linearly increasing ramp output. Okay, so an integrator is similar to a scalar, okay, except that the feedback component is a capacitor instead of a resistor. Okay, so how do we connect our components in an operational amplifier for it to operate as an integrator? Okay, so this is how a true integrator looks like. Okay, so instead of uh, a feedback resistor here or RF, we will be placing a capacitor instead. Okay, so we still have here your R and we have here our input, which is usually in DC. Okay, so how do we get the output, which is equivalent to 1 all over RC, negative 1 all over RC integral of VI, or the integral of your input dt. Okay, so usually we have here a negative sign because if you're going to look at your input, it is directly connected or applied at the inverting terminal of our operational amplifier. Thus, we have there your negative sign. Okay, so how do we derive the equation for our integrator circuit? Okay, so as you can see, our input there, okay, or our input current is equivalent to your I in. Okay, so that is equivalent to your I in, or your I input there is called your ICT. Okay, so that is your ICT. Okay, so that ICT current here, okay, so our input current here is the same as the output that will flow across our capacitor. Okay, why? So if you can still remember our virtual grounding, okay, so we said that there is no current that will enter our operational amplifier. So to do that, that will be your current entering or flowing across your R here is the same current that will flow across your capacitor there. Okay, so therefore those two currents are just equal. Okay, so we have to recall, okay, from your circuit analysis lecture. Okay, so what is the voltage relationship for a capacitor? So what is the voltage relationship for a capacitor? Okay, so the voltage relationship for a capacitor, or um, the current, okay, so the current, how do we solve for the current in a capacitor? So that is equivalent to the capacitance, okay, multiplied by the, okay, so the derivative of your VC or your voltage with respect to time. Okay, so for current to flow across your capacitor, there should be a change in voltage with respect to change in time. Okay, so you can remember this from your notes in your circuit analysis lecture. Okay, so getting now the values for your input and our output current, which happens to be equal, okay, so by nodal analysis, we know that your VI here, the input voltage, okay, minus from our point 2, let us call that point 2 equivalent to V2 divided by our R is equal to, okay, so the capacitance multiplied by the derivative of our so plus or minus, so that this is our V2, okay, minus, it is connected at our output, so that is equivalent to VOT, and then we have here your DT. Okay, so recalling again our virtual grounding, okay, so we also said that your V1 is equal to V2, or there is no voltage that will enter your operational amplifier. So therefore, in this formula, okay, our V2 is equal to 0. So our V2 here is equivalent to 0. Okay, so we have here your your VI with respect to time divided by our R is equal to C. Okay, so we have here a negative VOT. So let us just place the negative sign here. DVO or DV out all over DT. Okay, so to remove the derivative there, okay, so to remove our D there, we have to integrate both sides of our equations. Okay, so we need to integrate both sides of our equations. Okay, so from 0 to t. So from 0 to t. So we have here your dt, we have here your dt. Okay, so what happens now is this will be canceled out. Okay, so that will give us your output voltage. So that will give us your output voltage since R is a constant. Okay, so since R is a constant, we bring your capacitance here. So we have minus 1 all over RC. Okay, and then we have the integral of VI, the integral of your input, okay, dt from 0 to t. So this is the output voltage if we have an integrator. So if we place a capacitor in our feedback instead of a feedback resistor. Okay? So that is how we derived our equation. So we have here, what do we mean by true integrator? Okay, so what's the problem with a true integrator circuit? So we have here difficulties with true integrator circuit. Number one, operational amplifiers used in true integrator circuits must have extremely low DC offset voltage and bias currents. Okay, however, general purpose op amps are virtually unusable for true integration. Okay, so but we can have one special type of op amp. It is called a chopper stabilized amplifier, which uses a mechanical switching process to correct continually for offset and bias effects. Okay, so to eliminate these difficulties, okay, what we do is we have an AC integrator instead. Okay, so instead of just having, so it's like the true integrator is like a theoretical integrator circuit, but in practice, in reality, what we are using is an AC integrator circuit. So what's the difference? The only difference is that we are placing an RF or a feedback resistor, okay, which is in parallel with your capacitor. Okay? Because actually, if we don't have an RF here and you're really operating in DC condition, okay, so at a very, very low frequency, what happens to your capacitor at a very, very low frequency? So what happens to your capacitor is it becomes an open circuit. So this is just like an infinite circuit. So without this RF here, what happens is that you're just having an open loop. Okay, an open loop connection. Okay, so that open loop connection is no more an integrator circuit. So what we do is we place an RF here so that when your C here opens, okay, during DC, we have a finite value instead of an infinite, which is equivalent to that open circuit. Okay, so we use an RF in parallel with the capacitor to drop the gain to a finite value at DC, because at DC and without this RF here, we just have an open loop connection. Okay, so we have here the break frequency. So we need the break frequency so that we know when is the what frequency is your capacitor starts to operate. Okay, so we know in your previous discussions that your capacitor has something to do with the frequency of your circuit. Okay, so at a certain frequency, your capacitor will start to short out to become a short circuit. So without reaching that specific frequency, your capacitor is just acting like an open circuit. So what frequency is that? So we call that as your break frequency. Okay, so your break frequency is equivalent to 1 all over 2 pi RF multiplied by your capacitance, or that is just equivalent to the reciprocal of your time constant or your period, which is your TF there. Okay, so when your break frequency is much greater than the input frequency of your input signal, you have a gain. Okay, so you have a gain which is approximately equal to negative RF all over RI. So that means our capacitor or our integrator is just functioning as a normal. Okay, so it is functioning as a normal uh, normal inverting amplifier. Okay, so however, when your input frequency is greater than your break frequency, so that is the time when your operational amplifier is functioning as an integrator circuit. Okay, and for simplicity, we use a other books, other references, they use a prime here. Okay, so when you see a prime here, so that means we are using an AC integrator instead of a true integrator circuit. Okay, so this is the simple design procedure for an AC integrator circuit. Okay, so number one, we're going to assume that the desired processing function is so VOT prime. Okay, so that means we have a feedback resistor in parallel with your capacitance. Okay, is equivalent to negative 1 all over RIC. So your R here is the input resistance. Okay, integral of your V input dt. Okay, so the first step is you're going to select a fixed value of capacitor. Okay, so we are going to make use of high quality stable capacitors made of polystyrene or mylar. So these are the capacitors with no polarities. Okay, so we are going to make use here of a non-electrolytic capacitors. Okay, so the first thing to do is you have to choose. Okay, so as a designer, you can choose any value of capacitor that you want. Okay, so after choosing the value of your capacitor, we're going to solve for the resistor Ri. Okay, using this scalar factor here. So since K is equivalent to R1 multiplied by C, so Ri is equivalent to 1 all over the scale factor K multiplied by your chosen capacitor. Okay, so you can also choose Ri. So you can also choose Ri, and then finally you can solve for C. However, in practical circuit components availability, there are wider ranges of available resistors compared to capacitors. So there are only few available commercially used values for capacitor. So if you choose the value of R and resistors have tolerances, you can always choose those value that is closest to your actual um, actual solved value here. However, for capacitor, if we choose the exact resistance, we might have some difficulties in choosing the nearest value for the capacitance. So in practice, we choose the capacitor and then we just solve for R, and then we choose the closest value for an available commercially available value for a resistor. Okay, so we now have the two important components for your AC integrator circuit. You have now your RI and we have your C. So what is lacking is your feedback resistor. Okay, so there are two ways for you to solve for Ri. So first is using the time constant, which is equivalent to Rf, your time constant Tf divided by your chosen C, wherein your Tf is equivalent to 10 times your period or time your period. Okay, so lowest period. So that is your TL. So since we are afraid that at a lower frequency range, your capacitor is not yet turned on or it is not yet shorted, so we use the lowest frequency here. Okay, so wherein your TL is equivalent to 1 all over FL, wherein FL is your lowest frequency, the lowest input frequency of your input signal. Okay, so you can use the time constant or also you can use the formula for the break frequency. And the formula for break frequency is equivalent to 1 all over 2 pi FB multiplied by C, wherein your FB or break frequency is equal to 0.01 of your lowest frequency. Okay, so since we have here two formulas, okay, do not expect that they will yield the same result. Okay, so actually they will have a different value. Okay, so but you can use any of those two values, or if one value is an exact available resistor and the other one is not yet exact, so you may choose the exact one. Or if one value is very very high or very very low, so you have to choose the more practical value among the two. Okay, so if either or both of the resistance values are either excessively large or small, then we choose another value for their capacitor and then you start again with the procedure. Okay, so if your resistor computed resistance is too large, then you choose or increase the value of your capacitor and vice versa. So if it is too low, so you decrease the value of your chosen capacitor. Okay, so to summarize, all you have to do is to select or to design or to get the value for your three components. So your three components are the Ri, your C, and your RF. Actually, you just have to solve for the two resistors because you can choose the value for your capacitor. Okay? So, for practical application for integrator is it is used for wave shaping applications. Okay, so we have here an example wherein we get the value for the output peak to peak voltage, and the output peak to peak voltage is equivalent to K. Actually, your K is your 1 all over RC. Okay, so that is your scalar. Okay, so before so the scalar for the inverting and non-inverting is just your RF all over RI or RF all over RI plus 1. So our scalar here for an integrator is your negative 1 all over RC, although we don't need to place the negative sign there. Okay, so we need to compute. Okay, so for the net area, so we have your absolute value sign here, so that means we do not place the negative value, we just get the amplitude of the net area having the same signal. Okay, so what do we mean by this formula? Okay, so we have here an example. So it says here, the square wave below is applied to the input of an AC integrator with VOT, okay, with V output voltage equivalent to negative 1000. So this negative 1000 is your K. This is your scalar, okay? So after steady state conditions are established, determine the peak-to-peak output voltage and we have to plot it. Okay, so what we need to remember here is your output voltage. Okay, so what is our peak-to-peak output voltage? So your peak-to-peak output voltage here, so your peak-to-peak output voltage here is equivalent to K multiplied by the absolute value of the area. Okay, net area. Okay, so if you're going to look at the problem, it's like during positive half, you have your voltage as your, so it's like a rectangle. Okay, so wherein your amplitude is your height or length, uh, and the and the time, okay, or the period is your width. Okay, so having that shape, it's like our area is in the form of a rectangle, and the area for a rectangle is just length times width. So in this case, it is the amplitude, which is 10 volts, and the width, which is your uh, and the width, which is equivalent to your time or your period, that is equivalent to zero point 0.5 millisecond. Okay, so in this case, class, it is K. So your K is 1000. No need to place your negative sign there. And then your area is like 10 volts multiplied by zero point 0.5 millisecond. Okay, so if you're going to recall, what is our scalar? Okay, so what is our scalar for our integrator? This is equivalent to 1 all over RC. And we know that RC is time constant. Okay, so our unit there is what is time constant. So that is equivalent to seconds. So therefore, your millisecond here will be cancelled with your scalar here. So the output is just equivalent to volts. Okay, so your output voltage is of course in terms of voltage. So computing for this, our output peak-to-peak voltage is equivalent to 10 multiplied by zero point 0.5 millisecond, okay, multiplied by the scalar, which is 1000, and that is equivalent to 5 volts. Okay, so that is your peak-to-peak value. So how are we going to sketch our graph, or how are we going to plot our graph? So we said from our first slide that for an integrator with a DC input, you have a ramp as your output. Okay, so if our input, for example, is like this, so this is a negative, this is 10 volts, this is a negative going ramp, so therefore our ramp is going down. So for example, our input is like that. So this is your input here. This is your 10 volts like a DC. So this is up or upgoing, okay, or positive going. Your ramp will be like this one. Okay, so combining now the two so that we can plot. Okay, so an integrator, DC as your input and ramp as your output. So this is just like a DC because for the entire duration of your cycle, it is what, it is equivalent to 10 volts. For the entire duration of your cycle, this is equivalent to negative 10 volts. Okay, so if you're going to plot that now, your output will look like this. Okay, so this is your output looks like. So for positive 10 volts, so this is up going down, so we have a negative going ramp here, and this is up down going up, so we have a positive going ramp here. And our output is 5 volts peak to peak, so we have here positive 2.5 to negative, from 2.5 to negative 2.5, so that we can have a peak to peak value of 5 volts. Okay, so that is one practical application of an integrator. So why is it called a wave shaper? Because we change the wave or the shape of your waveform. Okay, so from a square wave or a rectangular wave as our input, we have a triangular waveform in our output. So we reshape your input signal. Okay, so if we want some applications that looks like this, therefore we can use an integrator circuit. Okay? So, aside from an integrator circuit, your can also operate as a differentiator. Okay, now, what does a differentiator do? Okay, so your differentiator is used to provide an output voltage which is proportional to the rate of the change of the input voltage. So, actually, your differentiator is just like the reverse of your integrator circuit. Okay, so this is the inverse mathematical operation to that of an integrator. So in this case, we have your ramp as an input, okay, or a change. You have a changing input, and then upon passing through a differentiator circuit, you will have a DC at the output. Okay, so it's the inverse mathematical operation for an integrator. So the output voltage is proportional to the derivative of the input voltage, the constant of proportionality or your scale factor, which is equivalent to negative RC. Okay, so how does this look like? Okay, so actually for a differentiator, we're just going to change the position of the capacitor. So instead of placing the capacitor in the feedback path between the input and the output, we will be placing your capacitor at the input terminal. So again, the input is still applied at the inverting terminal. Therefore, we still have a negative sign in our output formula. Okay? So how do we derive for the output voltage for a true differentiator circuit? Okay, so we have here again, so from the circuit, your ICT again is the same current that will pass through across your resistor. Okay, so for our input voltage, okay, so for our input voltage, and that is a capacitor, so your input voltage here is equivalent to what? Or sorry, your input current here, okay, is equivalent to C multiplied by the change in your input voltage divided by your change in time. Okay, and that is equal. So that is also equal to the output current, which is also your ICT. And since that is just a resistor, okay, so this is just a resistor, but your resistor is connected in a reverse polarity. So this is plus minus while this is a plus minus. So we have here plus and minus. So we have a negative at our input. So they don't have the same polarity. What is your current there? So your current there is your VOT or V multiplied by your um, V divided by R. Okay? So solving now for your output. Okay, so solving now for your output, we can place your R here. Okay, so we can um, cross multiply your R there. So we have your minus RC multiplied by dVI all over dt. So this is our formula. This is our output formula for our through differentiator circuit. So it says here that you should have a change in your input so that we can have your output here. Because when we don't have change in our input, our output is automatically equal to 0. Okay, so there must be a change or your input must not be equivalent to a DC source. So the amplitude response is very small. So the problem with true differentiator is that the amplitude response is very small at low frequencies, okay? But it increases linearly as the frequency increases. Okay, so we have here an example. We have here a true differentiator circuit produces an output voltage equivalent to dvi dt. So that means our K there is just equal to 1. So our RC there is just equal to 1. Okay, so where VI is the input voltage, so this is our input voltage. So the signal voltage at the left is applied as the input to a a differentiator circuit here. So let us sketch the output and label significant levels. Okay. So how are we going to compute for this? So how are we going to analyze this? Actually, this is just very simple. Okay. We have here, we will be analyzing each input. Okay, each inputs that we have. So for example, let us analyze our input from, so it represents change in voltage, which with respect to change in time, somewhat is like what? So it is just like a slope. Okay? So for example, we have from, so we have, for example, during the time from 0 to zero point 0.5 seconds. Okay, so what happens during the time from 0 to zero point 0.5 seconds? So we have your change in voltage, which with respect to change in time. Okay, so just like a slope. Okay, so you have your y and x. So your slope is from y2 minus y1, and then your x is x2 minus x1. So that will give you 6 minus 0. Okay, so from 0 to zero point 0.5, that is equivalent to zero point 0.5 minus 0. So this is your output voltage. Okay, so change in VI with respect to change in time. So 6 divided by zero point 0.5, that will give you 12 volts. Okay, now, how about from zero point 0.5, okay, to 4.5. Okay, so your output voltage from zero point 0.5 to 4.5 is, as you can see, there isn't any change from our from our voltage. Okay, so from this point, this is 6, and from this point, this is also 6. So that will give us 6 minus 6 divided by, we have here 4.5 minus zero point 0.5. But this is equal to 0. So automatically, from 4.5 seconds, from zero point 0.5 second to 4.5 seconds, we don't have an output voltage. Why? Because we don't have a change in our input. So for a differentiator circuit, you only have an output once you have a change in your input voltage. Okay, so let's continue from time. Okay, so from time, equivalent to 5 seconds, from 4.5 seconds to 5 seconds. Okay, so what is your voltage there? So your voltage there is from 0. So your output there is, your change in voltage is from 0 to 6. Okay, so 0 minus 6 divided by 5 minus 4.5. So in this case, we have negative 6 all over zero point 0.5. So this is equivalent to um, negative 12 volts per second. So we have here your so the unit is, since this is change in voltage with respect to change in time, so that is voltage divided by second. So these are the scenarios for our three different inputs. So this is your first input, that is a ramp. Okay, that is a positive going ramp. Our second case is that we have a DC as our input, so therefore there is no change in our input. And finally, we have a negative going ramp as in our output. So we have a negative here and we have a positive there, okay, per second. So what do we have there? How do we draw this? Okay, how do we sketch this? So this is now your answer. So from this, okay, so from 0 to 6, okay, or from 0 to zero point 0.5, we have here your 12 volts as your output, and then we don't have your output from zero point 0.5 to 4.5, and then finally we have a negative 12 output for a from 4.5 to 5 seconds. So again, we have a a differentiator circuit. Okay, so when you have a ramp as your input, you have a DC as your output. But if your input is DC, there is no change in input with respect to time, so your output is always equal to 0. So that is the application for a differentiator circuit. Okay, so the differentiator circuit can be used to detect sudden changes in a signal and to generate trigger voltage based on these signals. Okay, as the transition becomes sharper, the magnitude of the output voltage also increases. However, class, the problem with a differentiator circuit is that true differentiator circuits are not used often. Why? Because it is the noise tends to have a sudden abrupt changes. So how do we represent noise? So noise is represented as spikes, changing spikes like this one. Okay? So that means since noise is changing, your true differentiator circuit might be confused that your noise is your actual input signal, because the input signal for the signal for noise is changing. So for a true differentiator circuit, noise is accentuated. Okay. So thus, a true differentiator circuit is very noisy. Okay. So we don't want that type of amplifier circuit. So what do we do? So this difficulty may be alleviated by using a low frequency differentiator instead. So how does a low frequency differentiator uh, differs from a true differentiator circuit? So we just have to add. Okay, so earlier for the integrator circuit, we add a parallel resistor here, so no use. So we just place a capacitor here. Okay, so this is our solution for a low frequency differentiator circuit, so that our noise will not be accentuated. Okay, so the break frequency is equivalent to 1 all over 2 pi Ri multiplied by C. So this is now your scalar, Ri times C. Okay. So when your input frequency is greater than your break frequency, your capacitor is just like acting, or is acting just like a short circuit. No, so your formula is just, or your gain is just like a normal inverting amplifier. But when your frequency is much greater than your break frequency, your gain becomes 2 pi. So omega is 2 pi f, okay, multiplied by RF multiplied by C. Okay, so the design is just like what we had in our integrator circuit. So we're going to assume that the desired processing function is specified as VOT. So this time our K is RC. Previously our K is 1 all over RC. Okay, change in VIT dt. So let H, this time we are talking about the higher or the highest time period or the highest frequency. So for integrator, we are considering the lowest frequency. So for a differentiator, we are considering the highest frequency. Okay, so this is the reciprocal, which represents the period of the highest frequency component. So first, again, is we select the value for capacitor. So for the same reason as what we did in our integrator, because there are more available resistors compared to capacitors. So we just choose the value of your capacitor. Okay? So you have to select a fixed value of C. Do not use an electrolytic capacitor. So electrolytic capacitors, these are the capacitors which has polarity. So we use those with no polarities, or the non-electrolytic capacitors. Okay, unless the voltage across the capacitor always has one polarity. So from the desired value of K, so this time we can compute for RF. Okay, RF is equivalent to K all over C. So after solving for RF, we have to determine your RI. So this time, our RI is can be computed in two types. So in time constant criterion, so RI is equivalent to 0.01 of your TH all over C, or that is equivalent to 0.01 of FH all over C. or the break frequency criterion, which is equivalent to 1 all over 2 pi FBC, or so since this is higher, so that is 1 all over 2 pi 10 FH multiplied by C. Okay? So if either or both of the resistance values are excessively large or small, we change the value of capacitor and then repeat the entire design. Okay? So if the RS are too large, increase the value of your C and vice versa. So this is an example, okay? So a low frequency differentiator is desired for a particular application to perform the operation. So when you say design, okay, how do we design? So we design this in such a way that you have to supply the values for our three components. So what are those three components? So you have your capacitor, of course, you have your RF, of course, and then you have your RI. Okay, so the first thing to do, okay, so the first thing to do is we choose, okay, the value for our capacitor. Okay, so you have to you have to there are several sites where you can have your commercially available values for capacitors, or you can even look at your multi-sim, or even on in those values that we have used in our laboratory classes previously. Okay, so for example, I will be choosing the value for my capacitor. So this is just your choice. Okay, so you can choose any as long as it is a commercially available value for your capacitor. Okay, so for example, I will be choosing the value of a capacitor, electrolytic capacitor. Okay, so that is, for example, I will be choosing 1.1 microfarad. Okay, so there is zero point zero 0.01 microfarad, there is 0.001 microfarad, or there is 0.02 microfarad, 0.002 microfarad. So those are the different widely used values for capacitors. Okay, so for example, I will be choosing zero point 0.1 microfarad. So the first thing to do is I will be solving RF. Okay, so RF is equivalent to my capacitor divided by, sorry, the scale factor K divided by my chosen value for capacitor. Okay, so it says in the problem that your K is equivalent to 0.001. So that is your scalar. No need to place the negative sign. So the negative sign there just signifies that your input is applied at the inverting terminal. Okay, divided by zero point 0.1 microfarad. So where does the 1.1 microfarad came from? So I just chose that. Okay, so this will give me a value. Okay, solving for that. So that is 0.001 divide by um, zero point 0.1 micro farad, so that will give you 10 kilo ohms. Okay, so is there a commercially available resistor having a value of 10K? So of course there is. So therefore we can use RF be equal to 10 kilo ohms. Okay, then we choose RI. So we have two criterions in choosing your RI. So the first is using the time constant criterion. So our time constant criterion, so TH, your highest period is equivalent to 1 all over FH. So it says in the problem that the highest frequency there is 1 kilohertz. Okay, so therefore this is 1 all over 1K. So that will give you 1 millisecond. Okay, so in this case, solving for RI, that will give you 0.01 multiplied by 1 millisecond. So 0.01 multiplied by 1 millisecond based on our formula, divide by our capacitance, which is zero point 0.1 microfarad. Okay, so solving for this, you have 0.01 multiplied by 1 milli divide by zero point 0.1 micro. So that will give you 100 ohms. Okay, so is 100 ohms available? Of course. So if 10K is available, so as 100 ohms. But we still have our second criterion. So our second criterion is based on our break frequency. Okay, and your Ri based on your break frequency is equivalent to 1 all over 2 pi multiplied by 10 times your highest frequency, and that is equivalent to 1 kilohertz, okay, multiplied by our capacitance, which is 1.1 microfarad. Okay, so solving for this, we have 2 times pi times 10 times 1k times zero point 0.1 micro, okay, then we get the inverse of that. That will give you 159.15 ohms. Actually, the two values are not very, very far from each other, but since we're not yet sure if there is an exact value of 159, although there is a close value because there is a tolerance when it comes to resistance, we might as well choose the safer one, which is 100 ohms. Okay, so therefore, your Ri is 100 ohms, our capacitor is is zero point 0.1 microfarad, and finally our RF is 10 kilo ohms. So when you say design, all you have to do is to draw your differentiator circuit using these values. Okay, so we have here your answer. So this is your answer. Okay, so we have there your differentiator circuit. Okay. Then lastly, your operational amplifiers can also be used as a comparator. Okay. So when we say comparator, this from the term itself, it can compare. So it compares signal voltage. Okay, it compares a signal voltage on one input of an operational amplifier with a known voltage called a reference voltage on the other input. Okay, so it is nothing more than an open loop op amp with two analog inputs and a digital output. Okay, so you will be inputting an analog changing value for your voltage input, and then you have digital for your output. Okay, so the output may be positive or negative saturation voltage depending on which input is larger. Okay, so how does a how does a comparator looks like? So it says in our definition, it is just like a what? It is just like a open loop. Okay, so how does an open loop circuit looks like? So it is the one having no feedback. Okay, so when you have an input, you don't have an output. So we have here, for example, minus and plus. So this is the typical value. We usually place, for example, a reference voltage here. Okay, so let us say we have a reference voltage which is equivalent to 2 volts, and then we place your input here. So this is your input voltage, okay? So we have here, for example, positive 10 volts, and we have here negative 10 volts, and we have here your output voltage. So you can have an input which is analog or changing, and at the output, you just have two values. It's either 10 volts or just a negative 10 volts. So when your input is greater than 2 volts, okay, so you have an output which is equivalent to positive 10 volts. But when your input is lesser than 2 volts, you have an output which is equal to negative 10 volts. So you just have two values for your output. So you can have several input, but it will compare the comparator circuit will compare it with your reference voltage, which is 2 volts, and then will give you an output just the 10 volts if your input is greater than, or negative 10 volts if your input is less than. Okay, so we can also make use of zero as your reference. Okay, so when we use zero as your reference, it's just like you have your minus and plus. So we place your negative, your inverting terminal grounded. So that means, what do we mean by zero? By grounded, so it is zero, okay? And then we place your input here. We place your input here. And then you have your positive V here and your negative V here. So what does that mean? All values or all input that is greater than 0, okay, so all inputs that is greater than 0, we have an output that is equivalent to positive 10, and all inputs that is less than 0, you have an output which is equal to negative volts. So you have an AC as your input. So, for example, these are the values which are greater than 0. So, your output is equivalent to positive V. So, these are the values which are less than 0. So, therefore, your output is negative V. Okay? So, you have an analog signal for your input and you have a digital signal for your output. Okay? So, that is how an operator do, okay, or functions. So can you use these two inputs, both these two terminals, just for inputs? Okay, so can you use these two terminals just as an input? So yes, we also have this type of connection. Okay, so we have here, if we place here your negative input, and when we place here your positive input, okay, so we still have your positive V here and you still have your negative V here. So what will be your output? Okay, so it depends. Okay, so when your negative input here is has a greater value or a greater amplitude compared to this one, so we have an output which is equivalent to negative. But if it is of this of but if your non-inverting input is of higher magnitude compared to your inverting input, therefore you have a positive as your output. Okay, so that is how a comparator does. Okay, so usually this is being used in circuits wherein you have a reference voltage, and then when your input reaches this specific voltage, you have an actuator, you have a switch to be turned on, to be turned off, and so on. Okay, so that is how your comparator functions. Okay, so to summarize, we have from the negative scalar to a positive scalar to a unity gain amplifier, you have summing amplifier, you have different the subtractor. Okay, so you have integrator, you have differentiator, and then you have your comparator. So what did you notice? So your operational amplifiers can practically perform mathematical operations. Okay, so that is where the name operational amplifier came from. Okay, so before they really use it for mathematical operations, that's why it is called operational amplifiers. Okay, so that's it. Thank you for listening, and don't forget to hit the like button. Okay, so thank you very much and God bless. Okay, bye.